Hello. Today we shall study a special technique for integration called integration by parts. This is the beginning of chapter 7, section 7.1. Very effective, very powerful technique, which actually presents something like product rule for integration. We have product rule for differentiation, and now using it, we derive this special formula. So let's say you have two functions, u and v, which are functions of x, and we apply the product rule to the product, differentiate the product. We get u prime v plus u v prime. And now we integrate both sides of this equation. Integral uv prime dx equals integral u prime v dx plus integral u v prime dx. On the left side, integrating the derivative, you get just uv. And then we solve for uv prime. Solve for this term. And we can write now integral u v prime dx equals uv minus integral u prime v dx. Well, what you see here is the formula for integration by parts. Let's put it in green, very important formula. Okay, now remember again how we write differentials of functions. U prime dx, this is du, differential of function u. V prime dx, this is dv. If we replace this in the above formula, it can be written integral u dv equals uv minus integral v du. Looks sort of shorter and more symmetrical. Let's put this also in a box. It's the same formula written a little bit differently. When we use integration by parts, you have the freedom to choose either one of these two versions to apply it. Now, this is about integral without limits. What if we have limits? If we have limits, the formula looks this way. Let's say integral from a to b, u dv, this will be uv. This part is already integrated. We have to evaluate between a and b. And now we finish with this. So that's how it looks like when we use limits. Another green box. Here we go. Now I'm going to do examples to show you how effective is this formula. First of all, I want to explain that we don't use it each time when we have to solve integrals. We use it in special cases. So these are the two cases. Two cases for integration by parts. Well, we can use it in various situations, but these are the two cases which require integration by parts. Integrals of the form x to some power n, and here we have either exponential e to the x, or cosine x, or sine x, or with some coefficients. In this case, we take u to be the function x power n. Then u prime, let's say u prime will be nx n minus first, so the power is reduced, and we can repeat several times until x actually disappears. For instance, when n equals 1, and if you have u to be x, then u prime is just 1, x will disappear. So we shall study such cases, but I want to mention the other class of integrals first. Integrals like x to some power, which can be fractional, negative in the first case here, and has to be integer, and it's integer. Otherwise it doesn't work, but in the second case it can be anything. And then we have a function like logarithm x, or arc tangent x, or arc sine x, or arc cosine x. Function says that the derivative is more simple. So then we take u to be the logarithm, and then u prime is 1 over x. It simplifies considerably. If you have arctangent, if you take u to be arctangent, then u prime will be another simple function, a rational function. And with more practice you will see how to choose this quickly. If you make a wrong choice of u and v, your integral will go in a dead-end street. It will get more complicated. So the idea is this. We want to simplify the integral. In our formula, the integral that appears on the right side should be simpler. If you see that it's not getting simpler, then you're going in the wrong direction. So let's do examples now. Okay, starting with something simple. Solve integral x exponential 3x dx. Here, substitution will not help you. If you replace 3x by something, this x will stay as a factor in front, and you cannot integrate. Also remember that integrals do not have this property. If you have integral f g dx, this is not integral fx dx times integral gx dx. So you cannot just distribute the integration here. So how to solve this integral? We shall do integration by parts. I shall rewrite it here. And this is the first category where we have some power of x with exponential. So we take u to be x, then u prime will be 1 and x will disappear. Then v prime will be exponential 3x. I had to write v prime dx like dv. So what is v? We have to integrate this, and we do this in our head. Antiderivative of exponential 3x will be exponential 3x divided by 3. I told you to memorize such integrals, so you don't have to do it each time again and again. So we have u prime, v prime. All this work, all this preparation we do on the side in a box somewhere. We don't write this computation in front of the integral. We write here the solution. So we go now with uv. Look here, what is u, what is v. So we have x multiplied exponential 3x over 3 minus integral u prime v. No more x. So just v, and we can put 1/3 outside, like that. After applying the formula, that's what we get. And the integral which appears on the right side is much simpler. There is no more x here. And we can integrate. So this is x exponential 3x over 3 minus 1/3 exponential 3x over 3 and plus c at the end. And what can we do here? We can simplify a little bit. We can factor 1/3 exponential 3x. It's a common factor, and from the first term we have x minus 1 like that plus c. This is our answer. Okay, moving further. Another integration by parts. Let's say we have integral 5x sine pi x dx. Again, the first category. Some power of x with sine or exponential or cosine. So we take again u to be x or 5x. This 5 is unimportant. You can move it in front. But let's say you keep it inside, and then we take u to be 5x. U prime will be just 5. So then v prime will be sine pi x, and v integrating this, we get negative cosine pi x over pi. So here is my preparation. I'm writing now using the formula. My integral will be the product uv, so there will be negative 5x cosine pi x over pi, and minus integral u prime v. So this will be, there is a negative sign, let's put it here, 5 cosine pi x over pi dx. In the second integral, on the right side, there is no more x. Continuing this work, I can write here negative 5x cosine pi x over pi. Two negatives will be plus. Let's just simplify here for the moment. 5 over pi I can move outside. Cosine pi x dx. So this integral we can solve very easily. Continuing this work, negative 5x cosine pi x over pi plus 5 over pi. Integrating cosine pi x, we have sine pi x over pi and plus c. And here is the result, negative 5x cosine pi x over pi plus 5 sine pi x pi squared below plus c. This is our answer. Let's do one more, little bit more challenging. Integrate from 0 to pi, now with limits, 3x squared minus x times sine x dx. Now it's not just a single power of x here, but 3x squared minus x. Nevertheless, I shall take this again to be u, because when we differentiate it gets simpler. U prime will be just 6x. And the sign doesn't get simpler when you differentiate. It turns into cosine and then back to sine. This function is not getting simpler after differentiation. So this will be my u. V prime is sine x, so v itself will be negative cosine x. And I'm ready to start with my formula. So this equals the product uv. There is a negative in front. Let's put negative here. 3x squared minus x cosine x 0 pi. We have to put limits here because we have limits in the integral. And then minus integral 0 pi u prime v. You see, there are two negative signs here, so this becomes plus, and u prime is 6x, so I can put 6 outside, and it becomes here x cosine x dx. Okay, now this second integral on the right side, we cannot solve immediately. It also requires integration by parts. So we can do this separately. We choose some place on the left, and we do this integral 0 pi x cosine x dx. Integration by parts independently. U is x, u prime is 1, v prime is cosine x, v is sine x. Okay, so this integral will be uv x sine x between 0 and pi minus integral 0 pi u prime v, just sine x dx. And this will be. Now, evaluating x sine x between 0 and pi, we get actually 0 because sine pi is 0, sine 0 is 0, and this first term actually is 0, and we have integral only of sine x with minus, so this will be cosine x between 0 and pi. Cosine pi is negative 1, minus value of 1 is 1, and we get negative 2. Here, negative 2. So this integral here on the right side is negative 2. What is the value of our original integral? Let's finish the problem here below. Our integral, let's call it I equals, we have to evaluate this term here between 0 and pi. So we plug pi, we have negative 3 pi squared minus pi, cosine pi is negative 1, minus, and because you have one other minus in front, let's make it plus. When you said put 0 in the place of x, you get 0 everywhere. And the other integral was negative 2, so minus 2. And we just need to simplify this. This will be 3 pi squared minus pi minus 2. Well, we're coming to this number. You see these two negative signs will make plus. Very good. We did this integral. So if you have x squared with sine or cosine or exponential, we have to integrate by parts twice. Now it is good to move to the next type of integrals when we have logarithm or arc sine or arc cosine or arc tangent, and solve such one. Let's solve this. Integral natural log x over square root of x dx. We have power of x with logarithm. We can write this x negative 1/2 times natural log x dx. So what was the rule here with this type? We choose u to be natural log of x. Then u prime is 1 over x, which is simple function, the logarithm disappears. V prime here then will be, the other function will be x negative 1/2. And now we have to integrate this to find v. By the power rule, negative 1/2 plus 1 becomes plus 1/2. It will be x 1/2 divided by 1/2. So this is 2 times root of x. That's v. Okay, this preparation here on the side, I'm continuing my integral. I have to go uv. So this will be 2 root of x natural log x minus integral u prime v. I can put 2 outside. So here is v. And u prime is 1 over x. Let's put x in the denominator, dx. Okay, here we can reduce square root of x over x is 1 over square root of x. I'll just write it this way. 2 square root of x natural log x, rewriting, minus 2. And this will be x power negative 1/2 dx, reducing here. And continuing this work, 2 square root of 2 natural log x minus 2. And then we have this integration we already did. It's 1/2 divided by 1/2 plus c. So we have 2 root of x natural root of x minus 4 root of x plus c. We can factor root of x like that, and this will be natural log x minus 2 and then plus c. So we did this integral by choosing u to be the logarithm. Now you simply have no other choice. If you make choose u to be the other function, 1 over root of x, it simply differentiating and get more complicated, and you have to find v. That's really impossible. So make sure that when you work with integration by parts, you make the right choice. And I want to repeat, if you make the wrong choice, you get stuck. Another example. Solve integral with limits now from 1 to e x, let's say, power 20 natural log x dx. Don't be afraid by this high power here. That's a very simple integral. Okay, so we choose u to be natural log x. U prime is 1 over x. V prime is x power 20. We can integrate by the power rule. V itself will be x power 21 over 21. So we go now with the product uv. So this will be x power 21 natural log x over 21 between 1 and e minus integral 1e u prime v. I can put this coefficient 1 over 21 outside. And you see, u prime v, multiply these two, you actually divide by xv, so it becomes x power 20 dx, and that's all. The logarithm disappeared. That's it. Okay, evaluating the first term, logarithm e is 1. So we have e power 21 over 21. Then when you plug 1 in the place of x, logarithm 1 is 0, there is nothing else. The second term, 1 over 21, integrating x 20 power is x 21 over 21, and put limits 1e. So what we have now, this is e power 21 over 21 minus e power 21 over 21 squared, and that's it. That's it. We can, of course, factor and make it more simple, but that's not important. So I'll stop here. And now look at another one. Integral from 0 to 2 root of 3 arctangent x over 2 dx. Integrate with limits, and we're integrating just one single arctangent, and there is nothing else here. Well, then we can look, remember the formula where we have u dv and v du. Remember, I shall write it here below. U dv equals uv minus integral v du, with limits, of course. So it will be convenient here to take u to be arctangent, x over 2. So when you differentiate, the arctangent practically disappears. U prime will be 1 over 1 plus x over 2 squared, and by the chain rule, differentiate x over 2, get 1/2. So this is u prime. I will simplify it a little bit. There will be 1/2 1 over 1 plus x squared over 4. Write common denominator below, and 4 will jump on the top, reduced by 2. This will be 2 over 4 plus x squared. This is our u prime. And what is v? V is just x. So we're going now with our integral uv. So this is x arc tangent x over 2 between 0 and 2 root of 3 minus integral 0 to root of 3 v du. V is x, and we found u prime. So this will be here x, and there is 1, 2, which I shall put outside. Well, actually, I'll keep it inside, and we have 4 plus x squared dx, like that. Okay, moving further, evaluating the term here, the first term on the right. In the place of x, we put 2 root of 3. 2 root of 3 arctangent. When you divide by 2, it becomes root of 3, just this. At 0, this is 0. And what about this integral here? For the integral, we do substitution. U equals 4 plus x squared. And du is 2x dx, which is right on the top. So I'm writing here minus integral when x is 0, u is 4. When x is 2 root of 3, x squared will be 4 times 3 is 12, plus 4, 16, like that. And 2x dx, this is du, and here below you have just u. This is integral that follows. Continuing this work, let's see what is arctangent root of 3. We did this when we talked about inverse trigonometric functions. Tangent pi over 3 is root of 3, so arctangent root of 3 is pi over 3. We have 2 square root of 3 pi over 3 minus, here we have natural log u between 4 and 16. So this will be, let's write it this way, 2 pi root of 3 over 3 minus logarithm 16 over logarithm 4 will be logarithm 16 over 4 will be logarithm 4, just natural log 4, and that's it. Okay, we did this integration. Now I want to show you some more special cases. In the book you can see some examples where first you do substitution, and then we solve the integral. One example is this. Integral 0 pi exponential cosine t sine 2t dt. Variable is t inside an important hot letter. Now we have to solve this. We obviously have to do substitution first. Now we're using the letter u and in our formula, integration by parts, and writing u again here may be confusing. We may need another u. So I shall do w. W will be cosine t. This is my substitution. Okay. What will happen then with dt? I shall keep this a little bit, to do this a little bit later. First changing the limits. When cosine is 0, w is 1. Then we have negative 1. When t is pi, w will be negative 1. We have exponential power w. How to do with sine of 2t? Well, there is a formula which says that sine of 2t is 2 times sine t cosine t. Cosine t, that's our new variable, and sine t dt is, I'm writing it here, sine t dt. This is minus d cosine t, so this is negative dw. Everything is done. Well, we have to put these two outside, and our integral, let's call it y equals, I shall rewrite what I have, from 1 to negative 1, ew, and here to outside, sine t dt was negative dw, cosine is w, and here negative dw. I shall use the negative sign to switch the limits. So this becomes 2 from negative 1 to 1. W, E, W, D, W. And this was one of the first integrals which we did. X e to the x. So let's do it this way. I shall write this 2 times negative 1 to 1 w d exponential w, because exponential w d w, that's d exponential w, same derivative. So it will be u dv, this formula. According to this formula, I had to write the product, 2w e w negative 1 1 minus 2 integral e w dw. Second version of the formula. So this will be 2 plugging 1 e first power minus 2 plugging negative 1, here negative 1, e negative first, then minus 2. You see, integrating EW is the same, so you just go E1 minus E negative 1. And then this can be simplified. 2e first power, which is just e, plus 2 e negative first, minus 2 e first power, and plus 2 e negative first. After crossing out two terms, this will be 4 over e. 2e negative first plus 2e negative first, 4 times. Oh, that's what I get. Okay, let's do one more. Solve this until now without limits. Arc sine natural log x over x dx. Well, it looks quite scary with these two special functions, but it's actually a very simple integral. Obvious substitution comes to mind. We can put logarithm x to be new variable. And then again I shall use w here. W will be natural log x. dw will be 1 over x dx. It appears here, so all the integral becomes arc sine w dw. And then we used again the formula u dv. So this will be function u, and this is v. U dv is integral uv minus integral v du. So I'm going uv w arc sine w minus v du. So w, and the derivative of the arc sine will be root 1 minus w squared dw. For this second integral, we had to do a substitution. So I prefer to do it on the side. Let's take here w dw over square root 1 minus w squared. The substitution will be, oh, what letter now? Well, I shall go with u. We don't need u anymore above. So now u stands for this substitution, 1 minus w squared. So the u will be negative 2w dw, which appears here on the top. W dw, this is negative 1/2 du. The integral becomes a negative 1/2 outside du over root of u. So this will be negative 1/2 integral u negative 1/2 du. And this is by the power rule, negative 1/2 u 1/2 divided by 1/2, so multiply by 2 plus c. So this will be just negative root of u plus c. And now going back through all these variables, this is negative square root 1 minus w squared. And this, remember, this will be right here. This integral negative root 1 minus w squared. So the initial integral, again, let's call it j. This integral will be w arc sine w minus minus plus plus root 1 minus w squared plus c. And what was now w? W is logarithm x. So this will be natural log x arc sine natural log x plus root 1 minus natural log x squared and plus c. Well, that's it. That's how this goes. And what was funny in this situation here, we had to use different letters for substitution for the formula. You can use other letters, of course, so just be careful to return to the original variable at the end. Okay, now this was the lecture. Now I believe the homework will be quite doable, and you can spend 2 days on this homework. This is a relatively long topic. Goodbye.